Okay, so thank you very much, Tufik and the other organizers for this opportunity. So I'll be talking about a probabilistic bijection for non-attacking fillings, and this is joint work with my graduate student Zeus Dantas-Imora. So first I will define what is a probabilistic bijection. So we're all familiar with the classical notion of a weight-preserving bijection. So let's say we have two sets, A and B, and a weight function. It could be a different weight function, it doesn't matter. Uh, and we are considering the generating functions with respect to the weight function. And a weight-preserving bijection between A and B is a one-to-one correspondence such that the weight of the element in A is sent to the weight of the element in B by this function. And if such a bijection exists, then we can conclude that the generating functions are equal. Okay, so now let's say we know that we have two generating functions that are equal, but there does not exist a function that sends the weights from set A to set B. And even worse, what if the two sets have different cardinalities, so there doesn't exist any bijection at all? So what we can do is we can weaken the conditions of what it means to be a bijection. So in the classical case, we would call this the deterministic case. So we can write this bijection phi as a map F, which is essentially a matrix whose rows and columns are indexed by the elements in sets A and B. And the matrix entry ST is one whenever S is mapped to T by this function. So in the case of a bijection, of course, it has to be a permutation matrix. So there's a one in each row in each column. And then the inverse is represented by a second map G, and in this case, it's just the transpose of this matrix. Okay, so now the way we can relax our conditions is we can allow these maps F and G to have fractional values so that the row sum is still equal to 1 for every row. And essentially what this means is that we're sending a fraction of each element in A to the set of elements in B. And so we'll write this probabilistic bijection as a pair of maps, F tilde and G tilde. So F tilde is the map from A to B, and G tilde is the inverse map from B to A. And it satisfies the following conditions. So first of all, the total sum of the probabilities or fractions coming out of each element have to sum to 1. So that's what these conditions are. So that's why we call it a probability. And second, to preserve weights, we have to satisfy this balance condition on the weights. So essentially what this means is, so let's look at the right-hand side. So the weight of T1 is equal to the incoming weights from S1 and S2. And another way to think of this is as a Markov chain on a bipartite graph. And this is precisely the balance condition that one needs to conclude that a Markov chain has the stationary distribution given by weight. Okay, and so if there exists a probabilistic bijection between these two sets, then we can conclude that the generating functions are equal. And this is not too hard to prove. We just write down these sums and rearrange, and we'll get this equality. Okay, so here's an explicit example. So let's say my set A consists of these three objects, and my set B consists of these two objects. And these are just symbols representing some weights. And so we can see that the sum of all outgoing arrows from each object is 1. And then the balance condition is also satisfied. So if we look at, for instance, S2, so its weight, CE plus DF, is equal to the weight of T1, which is C, times the probability, which is E, plus the weight of T2, which is D, times the probability, which is F. And then the sum of the weights on the left-hand side is equal to the sum of the weights on the right-hand side, which is C plus D. So that's an example of a probabilistic bijection. Okay, so now part two. So here are the generating functions that we will be applying this to. So they're called permuted basement non-symmetric Macdonald polynomials, and we will write them as generating functions of objects that look like this. Okay, so this is not a talk about Macdonald polynomials, so I will just put this here to establish notation. So the symmetric Macdonald polynomials, P lambda, are indexed by partitions lambda, and these are a QT generalizations of the Schur functions that we just heard about. So they are an orthogonal basis for the ring of symmetric functions in parameters q and t. And when we set q and t to 0, we get back Schur functions. And then these generalize to the non-symmetric Macdonald polynomials, which are indexed by compositions alpha. And these form a basis for the entire polynomial ring in parameters q and t. And then these have a further generalization into these permuted basement Macdonald polynomials, which are additionally indexed by a permutation sigma that permutes the parts of alpha. So now we have these indices alpha and sigma. Okay, so we can write these polynomials as generating functions over tableau, over certain fillings, just like we saw with Schur functions, except these will be slightly more complicated. So taking a composition alpha, the diagram of alpha is a diagram whose column sizes are given by the parts of alpha. So here alpha is written here. So we have a column of size 2, a column of size 0, size 3, and so on. And the rows are numbered from bottom to top. And then the basement is an additional 0th row that we add to the bottom, and basement sigma, so sigma is a permutation, and it just means that we place the entries of sigma in the boxes of the basement. And now a pair of cells in this diagram is called attacking if it satisfies one of two conditions. So either the two cells are in the same row, or the two cells are in consecutive rows where the one above is strictly to the right. And then a tableau is a filling of this diagram with integers. So the integers actually have to be bounded by the size of the basement. And we say a filling is non-attacking if there are no repeated entries in attacking pairs. So can anyone spot the error in this filling that makes it attacking?
The two fours.
Oh,
Yes. Yes, the two fours. So these form an attacking pair, and so this is actually not a non-attacking filling, uh, but that's fine. Okay, so we will label the set of non-attacking fillings with basement sigma type alpha by NAF alpha sigma.
The integers in the
Okay,
filling are bounded by something, or you can fill it in anything.
yeah, they're bounded by the size of the basement.
Size of the basement. All right.
Okay, so the theorem, so this was a formula conjectured by Haglund. It generalizes the classical Haglund-Heyman-Lur tableau formulas for the Macdonald polynomials. Is that this polynomial E alpha sigma is a sum over the weights. It's a sum over all non-attacking fillings with a certain weight, and the weight is some rational function in Q and T. And we have these statistics, Madge and Cohen, that in a sense, generalize the permutation statistics Magin-Cohen. And here's an example of a filling and its weight, and then the content of the filling is as before. So it's just looking at the content of the non-basement entries. Okay, and so our main result is that if we have a composition alpha with two adjacent equal parts, so alpha I equals alpha I plus 1, then we can swap the basement entries in those columns and get the same weight. So this generalizes a result of Alexanderson, which proved it when these two entries differ by 1. And it also generalized an earlier result where alpha was just a partition. And so here's an example of this result. So on the left, we have all possible fillings with content 1, 2 for this shape, and there's two of them. And on the right, we have all possible fillings for this shape. So the set of fillings is limited by the non-attacking condition. And then you can check that the sum of the weights on the left-hand side equals the sum of the weights on the right-hand side. And so that is what we want. This equality is what we want to establish with our bijection. So we're going to construct a probabilistic bijection from the fillings on the left-hand side to the right-hand side. Okay, so here's how we will do that. So first of all, we need to swap the two entries in the basement. So now we might run into some problems. So first of all, this might significantly change the weight of the fillings. But even a bigger problem is that if the entries D and B are equal, then when we swap A and B, we're going to end up with an attacking configuration, which is not okay. So our solution is just to continue swapping at row 1 and then row 2 and so on. And we're going to accept all possible choices of whether or not we swap. So we're going to keep the filling where we stop at row 0, and then we keep the one where we stop at row 1, as long as these are non-attacking. And then we assign a probability to the choices made at each step in a way that takes care of the changing weights. And so we call probability TS to be the product of the probabilities for the choices made at each step. And we call this map rho, rho sub I. Okay, and here's an example of applying this map to swap the entries 3 and 2 in columns 3, 4 of this filling. So here are the three possible tableaux that we can get by performing these swaps. And here are the probabilities of reaching each of these tableaux. And then we can check that summing these three probabilities equals 1. And in fact, this map has an even stronger property where the weight from T to S times the probability from T to S equals the weight coming from the other direction. So this is an even stricter balance condition than the one that we required for this to be weight preserving, a probabilistic bijection. So here's this balance condition again. So if we think of this as a Markov chain, this is what's called detailed balance on the Markov chain. And so this also satisfies the more general balance condition that we had required for this to be probabilistic. And so we have a probabilistic bijection between these two sets, which establishes the equality of the generating functions. And so we are done. Okay, and here's back to our example that I showed before, except with the actual weights corresponding to these fillings. Okay, so to conclude, I will just mention that we can extend this idea of the probabilistic bijection even further to swap columns of different heights, and then we will end up with some new identities for the non-symmetric permuted basement Macdonald polynomials that show how to expand a polynomial into these polynomials of different shape. And that is all for my talk, so thank you very much.